In this video, we continue our presentation by discussing the shift registers. A shift register, by definition, is a register that can shift data either in one direction or in both directions. And the shift operation is controlled by a clock. Therefore, every clock pulse, the register shifts by 1 bit. The simplest shift register is shown in this figure below here, where this register shifts from left to right, as we can see here. So if the register contains 0, 1, 1, 0 as an example, at the clock pulse, either at the rising edge or at the falling usually, but this is for rising edge clock pulse, as we can see here, the data will be shifted to the right-hand side. So this 0 will be transmitted as serial output, and it is replaced by this one, which comes here, and this one will come here, and 0 will come here, and the serial input will come to the first flip-flop. Probably you will ask, why do we study shift registers? We give two for the shift register. The first example is for serial data transfer. And usually in communications, we operate in serial mode, which means data is transferred 1 bit at a time. Therefore, if we are talking about 1 million bits per second, it means the bits will go serially, one after the other, and each bit will need 1 microsecond to be transmitted. Let us take an example of the hardware needed to do serial data transfer. We assume that data is in shift register A initially, and this data will be transmitted bit by bit to another shift register B, where shift register B contents will be transmitted. So this is the serial out, and that's the serial in for shift register B, and this is serial out and serial in for shift register A. And as we have just mentioned, the shift will happen at the clock pulse. But in this case, if we would like to make shifts for a 4-bit shift register, so if these are 4 bits and these are 4 bits, we will need exactly 4 clock pulses to do that. We achieve this by ANDing the clock, which is continuous forever, with a shift control, and this circuit here will give exactly 4 clock pulses to shift register A and 4 clock pulses to shift register B. This is further illustrates as follows. This is the clock pulse with a period, as we can see here, and the frequency is proportional to the period inversely, and it continues forever, of course, as we have just mentioned. And the shift control is a time signal that has the duration of exactly 4 clock pulses, and it is 0 otherwise. So if we AND the shift control with the clock pulse, we will have 0 everywhere here, and then this is 0 multiplied by 0 here, and then it will pass to us 4 clock pulses, which is this one here, and this one here, and this the third one, and this is the fourth one, and it will continue 0 otherwise. So these are called timing signals, T1, T2, T3, 4. And at these timing signals, these 4 timing signals, this shift register will make the shifts. Let us give an. This is the same figure again, and we here assume that shift register A contains 1011 and shift register B contains 0010. So this here has 1011 and this has 0010. What happens after the first clock pulse? Of course, these are the initial values that we have just shown here in the figure up and in this table. After T1, as we have just mentioned, this bit will be transmitted, so this will disappear, will go out on the transmission line, and this is replaced by this one here, and this 0 comes here, this 0 comes here, and this 1 comes to shift register B. So this is from A to B now. And the shift register A will work circularly, so we call it circular shift. In other words, this bit here, the output of A, will go back to be the input of A. So shift register A will shift. This one comes here to this position, and this 0 comes here. This one comes here, and this one here comes back to from the left-hand side. So A will have 1101, and B will have 1001 after the first timing signal. We do this exactly 3 more times. So after T2, this 0 comes here, and this one comes here, and this one comes here, and this one goes to shift register B and also comes here in A. As far as B is concerned, this one will be transmitted, will disappear, and this 0 will replace the one here, and this 0 comes here, this one comes here, and in this position, we get the shift bit from A. So this is A and B after T2. We can continue exactly in the same way. After T3 now, we can go faster as a matter of fact. This bit will disappear. The 0 comes here, 1 comes here, 1 comes here, and this 0 comes here, and will also come here, and the 1 here comes this way, this way, this way. And finally, after T4, after the last timing signal, this 0 will disappear, and the 1 comes here, 1 comes here, 0 comes here, and this one comes to B, and A, this one comes here, this comes here, this 0 comes here, and this one goes here. So what happens after 4 o'clock pulses? Just to summarize, the contents of register A is transferred to register B. So this is no longer has 0010, it will have 1011, and the 0010 has already been transmitted on the line. And A retains its contents, which means A keeps its contents as they were before. That is the first example of using shift register for serial data transfer. The other example that we give today is doing serial addition. We have studied earlier to perform addition using parallel adders. As an example, if we have 4 bits register A3, A2, A1, A0, we want to add them with B3, B2, B1, B0. With parallel register, with parallel adder, we use 4 full adders. The first one to add A node and B node, second to A1 and B1, etc. We have discussed this before, and this is faster than the serial adder that we will take now. However, it will cost more logic. Now, the serial adders are different. It is slower in operation. However, it needs less hardware, which means with one full adder, we can share it now to add all the bits of A with the bits of B, as we will see next. Because it has this hardware, it will take more time, which means an n-bit addition will take n clock cycles. We will illustrate now how do we do this. Let's assume that shift register A contains the number, as an example, A node, A1, A2, and A3, and shift register B contains the number B node, B1, B2, and B3, and this is from least significant to most significant. What do? We connect the shift out of register A and register B to the inputs X and Y of the full adder. And then the input Z of the full adder, we connect it to the output of a flip-flop, which we call Q flip-flop. It is of D type, and this flip-flop is cleared initially, so we have 0 here, and as you can see, this has a direct clear input as we studied before in the D flip-flops. Now, the operation is performed as follows. We have a common clock, and this common clock is similar to what we have just described, which is ANDing the normal clock together with the shift control, which is 4 clock pulses duration, as we have just described. Therefore, these two signals are the common clock and the shift control, which are ANDed together. so that this flip-flop is changed exactly for 4 clock pulses. Now what will happen is the following. At the beginning, we have A naught here and A B naught here, and the carry is 0. So this adder will add A naught plus B naught plus 0. The sum will appear here, which we can call S naught, and the carry, which will be considered next time, we call it C1. So C1 will be here, and S naught will come here. Now, what will happen? At the clock pulse exactly, shift register A will shift and B will shift, which means A naught will disappear, B naught will disappear, and the inputs to A and B will be as follows. S naught will be input here. So after the first clock pulse, after T naught, we have shift register A will contain S naught, then A3, A2, A1, and shift register B will contain B1, B2, B3, and whatever we have inputted here as serial input. So let's call it X. And the carry flip-flop here will be loaded with C1. Then, as soon as this happens, we find A1 is here, and B1 is here, and C1 is here now. So we add C1 with A1 with B1, S1 will be here, and C2 will be here, and C2 will come here, and S1 will be input here. Again, at the next clock pulse, what will happen? A1 will disappear, and register A will contain A2, this will disappear, A2, A3, S naught, and then S1. Shift register B will contain B2, B3, and whatever it has been input through the serial input here. When that happened, this will be A2 here, and this will be B2 here, and then C2 will be the carry, and in the next time, sum 2 will appear here, and C3 will appear here, and sum 2 will come here. And then after the third clock pulse, A will contain A3, S naught, S1, S2. And B will contain B3 and whatever was input through the serial input. Finally, at the fourth clock pulse, A will contain S naught, S1, S2, and S3, and B will contain 4 new inputs that we can possibly add with the sum if we want. So this explains completely the serial addition operation. To summarize this very briefly now, we have one number in A, one number in B. We send the bits of A and B 1 bit at every clock pulse. So the first clock pulse, it adds A naught plus B naught plus 0. Second clock pulse, it adds A1 plus B1 plus C1. Third clock pulse, A2 plus B2 plus C3. And the last clock pulse, it adds A3 plus B3 plus the carry from here. And the sum was inserted into register A 1 bit at a time, which means 1 bit at every clock pulse. At the end of the operation, register B will contain 4 new bits, and register A will contain the sum of A and B.